And we are live. Hi, ast111x. My name is Frank.
I'm Bill.
And I'm Tom.
And we're going to chat for about an hour, talking about some of the questions that were posed on the discussion board after we introduce ourselves. Then we may have some presentations, may talk a little bit about some of the questions that have come up in the course and just some general guidance. So if you're watching this, all 16 of you who are watching right now, go ahead and you can't type in questions live, but you can go to our course website and type in a question in that discussion board area, and we'll pick it up as we go, and we'll just sort of answer it live as we go. So my name's Frank. I'm the instructor for the course. What do I do? I like stars. I particularly like blowing them up. So I think that'll be one of the questions that came up in the discussion, is some new thing that blew up and why that's of interest. So I'll talk a little bit about that when we get there. That's a little bit about me.
All right, I'm Bill Wolf. I'm a postdoc at Arizona State University. I actually work with Frank. I also like stars and blowing them up in various ways, although we find unique and different ways to blow them up between the two of us. But I'm mostly doing theory work on a computer and trying to compare to observations.
Bill does the cool ones. I just sort of do the ugly ones. But yeah, in case you hadn't noticed, I'm a theorist too. So you get two theorists going here.
And I'm Tom. In my previous life, I was an electrical engineer, and my hobby was amateur astronomy. And about 6 years ago, I decided to stop doing electrical engineering work and go back to school and get a PhD in astrophysics. And so just this past August, I defended, and yay!
It's Dr. Tom now. It's Dr. Tom.
Yeah, it's all over but the cap and gown.
Yeah, that is awesome. Congratulations.
Yeah, thank you.
Very cool. Okay, why don't we go ahead and start in on some of the questions that people have asked in the discussion board on questions for our topics. Yeah, let's see what we got. So Tom, why don't you go ahead and pick one and we'll roll from there.
Okay. One of the first questions was about planet 9. And let's see if I can switch over.
See a picture of planet 9.
There we go. Yeah, there's a lot of talk about planet 9 because the trans-Neptunian objects that have been identified, the theory says that those orbits should have become unstable, and those planets should have been ejected a long time ago. I'm sorry, not planets, objects. Those trans-Neptunian objects should have been ejected a long time ago. But if you have a big object like planet 9 in just the right orbit, that could act as a stabilizing factor to keep those planets at home. So there's a lot of discussion about what planet 9 could be. Where is it? What does the orbit look like? How do we find it? As you can see in this diagram, it's not completely to scale, I don't think. But they're estimating that the orbital radius of that object is somewhere between 200 and 700 astronomical units. And Neptune is out there at about 30 AU over here. So this thing is really far away. And being far away, that means it has a very long orbital period. It's estimated it might be 10,000 to 20,000 years. So finding this thing is going to be very tough because it's so far. Well, we don't know if it's close or if it's far away at the present. So the search is on to train some telescopes to see if we can see an object moving very slowly. Some people have postulated that we might have taken a picture of it already in old photographic plates. So some type of computerized search should be done to go through all those plates that are, I think they're transferred to digital media now, but to see if they can find something that's moving very slowly from year to year.
Hey, Tom, what's a plate?
Ah, a photographic plate. Yeah,
Ah.
yeah. Back in the old days when they didn't have CCD cameras, they used film.
Film? Oh my gosh!
And yeah, sometimes the film was on glass. So those things last forever, but they're not very. Reading them is very manual and takes a long time. So if you imagine we found Planet 9 and we looked at it for 10 years, and the orbital period is 10,000 years, that would give us 0.1% of its orbit. So any errors you made in the position of that planet, or estimating the position, would lead to great errors in the orbit. So if we do find it, it is going to be hard to pin down the exact orbit of that planet for some time. Let's see. So that's all I have to say about it right now.
What's your bet? What's your bet on what year will it be detected, if at all?
Ooh, I would say within 5 years.
5? Okay. All right.
That's my wild guess.
So your gut tells you it's real.
I would think so.
Okay.
There would have to be. It seems to make sense that there's something out there. And let's see, by the way, I think they're estimating that it would have to be somewhere around 10 Earth masses. So that would be a good-sized planet.
Mm-hmm. Hey, aren't the protagonists in this story the same characters that killed Pluto?
Yeah, once we identify it, then we might have to think about what we call it.
No, I mean that the protagonist in this story of Planet 9.
Oh, just as a replacement.
Or one of them is one of the main instigators for why Pluto was changed classifications.
Oh, so he has some guilt there and wants to
guilt
make
and
amends.
Coming back to reassume Planet 9.
Yeah, I'm guessing if it does follow an orbit that's projected like that, oh boy, what do you call that thing? It's like a rogue shepherd planet or something.
That'll create all kinds of
yeah,
fun naming conventions for that thing.
But yeah, we didn't
just call it Planet 9 and be done with it.
we didn't even know Pluto's orbit exactly until New Horizons came and made a visit and got that more accurate.
Yes, I know.
So Planet 9.
Unfortunate video remembrances of making some now errant statements about Pluto. Oh, goodness. Cool. Yep, Planet 9.
I'm sure we'll hear more about that in the news.
It'll be coming. Bill, you want to pick one?
Sure. I see there's this question here, I believe, from Mohammed Sis from a few days ago. Very short, poignant question. We got the full moon every 27th of the month. So it's sort of asking, if the moon's sidereal period, the time it takes to make one full revolution around the Earth is 27 days or 27.3, shouldn't we get the full moon on the 27th of every month? The short answer is no. There are actually a bunch of different months. The sidereal month is just one of the different ways of measuring what we call a month. It's kind of, if you go on Wikipedia and look up lunar month, I think there's actually 5 different words. I was not familiar with several of these, but the two that are most interesting are the sidereal month, which is what we've been talking about, which is, if you attached a rod from the moon to the Earth and had it go all the way around, when would it have 360 degrees? When in space has it gone around 360 degrees around the Earth? And that's around 27.3 days. Then there's also the synodic month, which is probably what we are more accustomed to by looking at the moon. That's the amount of time it takes the moon to go from being directly between or nearly directly between the Earth and the Sun, basically a new moon, to the next time that it does so. And that is about 2.5 days longer, or a little more than 2 days longer, I think 29.5 days. And that is because while the moon is going around the Earth is going around the Sun. And so it actually has to go a little bit further than 360 degrees around the Earth to match up with the Sun again. Okay, so would we have the full moon every 29 days? Well, yes, we do, but it isn't necessarily, the 27th or the 29th of the month, because if you look at the calendar, at least the calendar we use here, it is not based on the moon anymore. It seems somewhat randomly, some collection of 28, 30, or 31 days. So since those numbers aren't commensurate, where these phases of the moon fall on our actual calendar month is going to mess around from month to month. But different cultures actually still use month-based calendars where the first day of the month is defined as when you see the very first sliver of the first quarter of the moon. And in that case, you probably do have more accurate, the somewhere in the half of the month is always going to be a full moon. But most of us, at least in the Western world, are still using a synodic calendar that's looking at the sun and the seasons to try and make sure things don't slip and are more consistent on the year. The bad side of that is the phases of the moon are no longer fixed on any day of the calendar month.
Cool. Okay. Yeah, time permitting, I may hit some of that. Let's see. Have a question from Elizabeth on what is your opinion on this latest astronomy discovery? And there's a link there to the now famous neutron star collision gravitational wave light. What the heck is that all about? Okay. Well, I have some facts and then I have some opinions, but we'll try and stick with the facts before I speculate. Yeah, so that story actually starts about 35 years ago, when some folks had the wild idea that you could detect space waving around. You could measure the distortions of space-time from mass moving within the universe. So it takes some pretty concentrated forms of mass, i.e. things like black holes, to get enough mass in one area to make space wiggle around enough that you could possibly detect it. But the funding agencies thought that was a great idea. And so particularly the National Science Foundation. So they've been funding this idea that you should be able to catch gravitational waves for the last 40 years. It costs about $1 billion. It's over 40 years, so it's not that amazing. And just to give you a sense of the size of the effect, when black holes merge or collide and they make space wiggle, that wiggling of the space, the length scale that you have to measure is on the order of the size of a proton. Okay, so very small effect, and that's just because gravity is a weak force. So people have been searching for 40 years, and then about 8 months ago, the news amazingly came through. Oh, and by the way, there are now 3 of these detectors. One of them is in Louisiana, one of them is in Washington State. And about 8 months ago, the very first detections of gravitational waves were made from stellar mass black holes merging. And you could catch the fabric of space-time wiggling around as those 2 black holes became one black hole. So that was about 8 months ago or so. In the interim 8 months, there's been 3 other detections also of black holes merging. So what these are showing is black holes are real. They're no longer a theorist's imagination. They're quite real. And they're dynamic, and they come in pairs at times, and those pairs can merge to make bigger black holes. So the expectation is that when you merge black holes, that you're not going to see any light off of them. There's no electromagnetic signal coming off. There's no photons coming off because they're black holes. So that didn't, but that was a prediction. And so people, of course, looked. They didn't find any light from these merging black holes. There was no radiative counterpart. So far, so good. And then around mid-August of this year, right about the time that the solar eclipse was happening, the gravitational wave detectors wiggled, and they wiggled in an unusual way, indicating that it was not two black holes that were merging, but it was two neutron stars. So a neutron star is the densest form of matter known. If you go any denser, it does turn into a black hole. And they immediately alerted other observers who look for the photons from said events, and they quickly located it. They got it within the right galaxy. They even got images of the actual explosion, if you like. And so that is what has been made the news in the last, since Monday the 16th, is the detection, the very first detection of neutron stars colliding. So why is that important? Well, at a meta level, anytime you open up an instrument that you've never looked at before, you find new things about the universe. And so that in and of itself is satisfies our passionate curiosity about the universe we live in. But also, where does gold come from? Where does silver come from? Where does platinum come from? This has been a mystery for a long time. The general idea of how you make gold is fairly well known. How you make silver is fairly well known, but nobody had been able to identify the actual origin side of these things. So when you take two neutron stars and you smash them together, you're going to make all kinds of material that will yield gold and silver and thorium and uranium and lead and all those heavy elements above iron. So in other words, and this is in some of the press reports, is gold is produced by neutron star collisions. That's at least partially true. So those are the facts and why it's important, why the neutron star is important, because basically it's going to make partly you and me coming out of those collisions. That gold in our body may well be from neutron star collisions. So we're part of this game. And in my opinion, since that's what you asked for, my opinion is the pendulum will probably swing a little bit too much to one side, then that the claim will be that all gold comes from neutron star mergers. And all is a pretty strong word. I think there are other potential sites that may contribute. So we shall see. But nevertheless, we've certainly identified one, and that's a huge, huge step. So this is like one of those moments over the past year with the detection of gravitational waves that are sort of watershed moments in science. Exoplanets was a watershed moment, and the detection of gravitational waves is a watershed moment in science, in our understanding. So that's my yammering about that topic.
Just to throw in there,
yeah, please.
Yeah, the other black hole mergers that they identified, they didn't have any optical counterparts, because I think they only had, what, 2 of them operational at the time? And
to which?
Two interferometers, 2 detectors.
Oh, gravitational wave, yes.
Yeah, and they couldn't really specify the position. And
oh, got it. Yeah, the air box that you had to look in was ginormous. It didn't constrain the area on the sky that you had to look at very well.
There's like a treasure chest somewhere in the Atlantic Ocean. That was about as helpful.
Go find it. It's there.
Yeah, but on this one, they could find that elliptical galaxy, that old elliptical galaxy where they think it came from.
Mm-hmm.
I'm not sure exactly how they are 100% certain that it came from that elliptical galaxy, other than sure seems like a likely candidate, or maybe the distance matched.
The distance was
That
relatively
could
close,
that
and
could be
people
it.
had several images of the galaxy before the explosion. So it's just like hunting a supernova, right? You have a normal galaxy, and
Yeah.
then you take a picture now, and there's a bright dot. Whoa! Except this one was not a supernova. This one was something special. So yeah, they had before and after images. They actually caught it with light, you know, on the rise and fade of the light curve, how much light was coming off the thing.
Yeah,
Are
just
there-
just the sensitivity of that detector is amazing. I think they said they can detect something on the order of a 10,000th of the diameter of the proton, which just I can see why Einstein was pretty convinced that people would never detect these things.
Yeah,
That's
incredibly small.
amazing.
It's amazing. It's amazing.
Frank, did you have any other favorite sources for heavy elements that you think might be getting the short shrift here?
Well, okay. To make gold, to make silver, to make uranium, the way you make that is you start with a very common element like iron, and onto that iron you add neutrons. And so occasionally one of those neutrons will turn into a proton, and that's how you build up everything heavier than iron, is basically by neutron addition. So if you want to add neutrons, you got to go where the neutrons are. So one possibility for where the neutrons are is in a supernovae. When you first form one of those neutron stars, there's certainly a lot of neutrons around a neutron star as that thing collapses down into a neutron star. So that has been traditionally the favored site. It hasn't really worked. You have to kind of tune it a lot, and anytime you have to start fine-tuning a model too much, that's usually not how nature works. And I think we're seeing that this week with the circles on circles on circles cosmology, right, and the replacement from Copernicus. So if you want neutron addition, really go where the neutrons are, and that's in an entire neutron star. You've basically got one huge neutron the size of Phoenix or the size of Chicago. And when you smack it into another neutron about the same size, boy, that's going to give you a whopping amount of neutron to do something with, to add on to iron. So I don't think that my opinion is that the supernova game is not over yet. I don't think it's dead yet. There may be particular regions of that heavy element spectrum that are better suited to supernovae, but maybe not. So we shall see. I just wouldn't count it out completely yet. I understand there will be this big sociological rush of, it's neutron stars, everything. Maybe, maybe. So the other scenario I would not count out yet is still the explosion of massive stars and the creation of those neutron stars. That's opinion. Thank you for leading me into that hatchet room. Okay, any other questions we should answer on the boards? Let's see what we got. What do we got?
So we have this one from Jose about the moon. We weren't quite certain.
Oh yeah,
what the problem was.
Looks like we've got two new ones too. Yeah, Jose had given a description about phases of the moon, and I have to admit that at least I did. I had to scratch my head a little bit. I'm not quite sure I understand what is being described and what exactly the mystery is. But we have some potential ideas. Do you want to say anything about libration, Tom, or let it roll?
Yeah, I'll go find my my web page that might have something on that.
Yeah, so actually all three of us looked at this and couldn't quite make out what was being asked. It's possible what is being asked is a phenomena known as libration. And when Tom finds his Uber cool little animation there. We'll show you what libration looks like.
I have to share first. Okay, so there's a view of the moon going through the phases, and I'm not sure if he was asking if the same 10% of the moon was always hidden when it's in the when it's mostly illuminated.
Yeah, I can't answer that. I don't know. But
Yeah,
but what in this image sequence you're showing, what is libration? Just what is the phenomena? No explanation needed. Just what is it? What part of that is the libration?
Yeah, I think that's from the tilt of the moon's orbit, right?
Yeah, but what is libration is the wobbling of the moon, apparent wobbling of the moon.
Okay, yeah, I'm not that familiar with it.
Okay, so notice that when you look at that image he's got, of course you can't see it if I don't shut up. The moon seems to get bigger and smaller, and it also seems to wobble. That whole phenomena is known as a very fancy term called libration. And why that is beyond the scope of this course, but it's easy to observe, and it's called libration. But we're not really sure that that's exactly what the question is asking, so we have asked. It looks like we got 2 new questions coming in. I'll take one of them from Ankurmar. Sorry if I butchered that name. I think that's right. Ankurmar. And the question is it possible that 2 black holes merged and became nothing? No. Short answer. If 2 black holes merged, they became 1 black hole. They still have mass, right? Well, the distinguishing properties, a black hole only has 3 properties, okay? Only 3. A black hole has mass, meaning it has gravity. So if you're far away, it's just like any other gravitational mass. So black holes have mass. Black holes have spin. They turn. They have angular momentum, if you like. And potentially they have charge. You can put a charge on a black hole. Nobody's ever observed a charged black hole, like a positively charged black hole and a negatively charged black hole. But in principle, a black hole can have charge. So those are the only 3 properties a black hole can have. And so you can't take those properties, particularly mass, and make them just vanish. That would violate something, right? By conservation of energy or conservation of goodness, or I don't know what. But no, they become a single black hole. The masses add. So if each one was a 1 solar mass black hole, then you have a 2 solar mass black hole. If they both have spin, and most things in the universe do spin, then those spins will add. Just leave it at that. And if they had charge, then the charges would add. Okay. So it became something. It became a larger, more voracious black hole.
I can try and take this other question here from, is it JLH17, just a few minutes ago. What is dark matter and why are we unable to detect it? So first off, dark matter is thought to be something that has mass, and that's why we're calling it matter, but it's dark and that we can't see it. It does not emit or reflect or block light, so it's dark. It doesn't interact with light in any way whatsoever, but it does interact with us gravitationally. The second part, why can't we detect it, is a little bit misleading. We actually do detect it in some ways. We just can't see it literally reflecting light through a telescope, but we can see its effect on things. So for instance, if you look through the Milky Way and with the telescope and try your best, and this will sound crude, but astronomers are good at this, of like counting all the stuff. How much matter do we see, or accounting for the things that we think we can't see. And the best we come up with still seems like it's way too little mass to explain how rapidly things are revolving around the galaxy. So we've been talking this week about Kepler's law, and you can look at the orbits of these things and actually ascertain this mass, m1 plus m2, that we had in in Newton's form of Kepler's third law. But if you do that with all the mass that we think we can account for, things seem to be rotating revolving way more rapidly than they should be. And so it was proposed that there must be some other form of matter that we can't account for and that we're just sort of calling dark matter. There's other evidence for this too in other galaxies and other surveys, and using dark matter in simulations of the universe actually ends up explaining some of the large-scale structure pretty nicely, but there are still some other questions. So yeah, we can't see it, but we do detect what it's doing to the universe and how it's affecting us in our galaxy as well as galaxies around the universe.
Okay, so I asked Thomas, I'll ask you, what's your bet on when dark matter will be detected, if ever?
Me, if dark matter is detected?
Mm-hmm.
I don't think they're going to detect that anytime soon. I know some people, so I had several people that went to graduate school with me that, you know, they went down into the deep coal mines. They have these amazingly sensitive experiments to test these different models for what the physical makeup for dark matter can be. So they think it interacts with the weak nuclear force, which is also beyond the scope of this course. But they've got these nifty techniques, but they need to get really far away from civilization. They go down to these abandoned coal mines, and they keep having, you know, result after result, and it's always, we found nothing. And I think with the latest ones, they would expect there to be, I don't know, on the order of like a detection a year or something. I can't, give or take. I can't remember the order's magnitude. So if it is this model that they think, this weakly interacting massive particles, and the way they think they work, WIMPs, then it should be within the order of, I don't know, a few years. But I don't know. My gut feeling is you're not going to detect that in my lifetime. But I think I just like the mystery of dark matter. It's just this bucket of matter. I believe by mass we think dark matter outnumbers, you know, traditional baryonic matter, like 4 to 1 or something. There's much more dark matter, much more mass in dark matter than there is in protons and neutrons. So it's a big deal, and I don't know. I kind of like the idea of that being unknown.
You're a mystery lover.
The latest wild idea I've heard is that people are speculating that maybe it's evaporated black holes that have a very small radius but are still massive. So, but yeah, that's going to be a hard one to find, I think.
Okay. So the general ordering I'm hearing is Planet 9 before dark matter.
I would agree.
Yeah.
Okay. Let's see. We got another question. Is what causes tidal locking? Also from JLH17. What causes tidal locking, and how common is it among planets and moons? Tidal. We are actually going to cover this. I believe we actually cover this week. Actually,
yes.
We talk about tides. So tidal locking is caused by tides. The simple version of it is that a moon and a planet is trying to equalize the force between them. So when all the forces balance with each other, they get tidally locked. That's a little loose, but it's okay. But it's extremely common. Tidal locking happens all the time. It's a very natural consequence of planets and moons to always have one body or both bodies face each other. Either one body has the same face toward the other, or they both have the same face toward each other. So tidal locking is caused by tides.
That's the name.
That's right. And it's a gravitational force acting on asymmetries in a body, right? So the reason it works on the Earth is because the Earth is not a perfect sphere. We have a bulge from the fact that we spin, and that bulge interacts gravitationally with the moon, and that's what causes the moon to always face one side toward us. It's what causes the moon to be slowly drifting away from the Earth at about 1 centimeter or so per year. It's also what's responsible for the Earth slowing down its rotation rate, so the day's getting longer. And I think the equilibrium spot for the Earth and Moon is of order, if I remember right, order 10 to the 10 years or so, if nothing else got in the way. And then the day would be, if I remember right, on the order of about 50 days. And then the Moon and the Earth, there would be no more tides, and the Earth and Moon would face one another, and they'd be happy. They'd reach an equilibrium situation. Right now, it's not an equilibrium. It's a dynamical situation. It just takes a long time. Okay, that's
the other part of that question is how common is it among planets and moons?
Mm-hmm.
I don't really know. Is that, I mean, that if something isn't tidally locked, it's always in the process of happening. It's whether or not, you know, it just so happens that the moon and Earth will do this right about the same time that they get incinerated by the expanding sun.
Right.
Are like Phobos and Deimos tidally locked? Is Io tidally locked?
I know Charon and Pluto are. I know that Io and Jupiter are. And I would bet dollars to donuts other ones are as well. I just don't know them off the top of my head. That's okay. So let's take it. Okay, I'll take that as a homework question. How many planets in the solar system or moons in the solar system are tidally locked to their host planet?
Well, and is sorry, I'm running away with this. Is Mercury's in some sort of weird pseudo lock? Is it in like a resonance with the sun where it rotates 3 times for every 2 times it revolves?
That's correct.
Like, that is
not
stable.
a tidal lock. It's a funky orbital resonance.
Okay.
Right. In fact, yeah, I could actually put that up. What is the time scale for tidal locking? And Mercury's on the cusp. Yeah, okay. I'll take that as a homework question. Fair enough. Okay, you win, JLH17. Boo on you. Wait till you see the response. Okay. I think that's it. Where are we at? We are at about 10:40 or so. So why don't we do a little presentation stuff. Tom, you got some stuff on telescopes?
Sure.
Okay. No rush.
Okay, so I'll talk a little bit about telescope recommendations and what to see outside in the night sky. I know everybody is interested in learning all about the physics of solar systems, but everyone also wants to know a little bit more about what's up in our own sky. So here are a few recommendations and how to find, once you have a telescope or some type of viewing instrument, how to go find things, how to know what you're looking at. Okay, so first of all, darkness is everything. You can't see very much from the middle of downtown Chicago or downtown New York. Even downtown Phoenix isn't good. The eye really needs about 30 minutes of darkness to dark adapt. That means, you know, just like when you get a flash from a photo, someone's taking your picture and a flash goes off, you can't see for a while. So you're in the dark, you're looking at the sky at very faint objects, so you want that flash effect to completely go away. You want the rods in your eye that are sensitive to black and white, you want those to recharge so that they're not saturated from a previous response. And that takes about 30 minutes of not looking at your cell phone, not looking at a light in the distance. Even the full moon is bad. So if you ever are out with a telescope, you'll see people with dim red colored flashlights because the red doesn't seem to wreck your night vision. Okay, and definitely travel away from city lights and bring a friend for safety reasons. You don't want to twist an ankle out in the dark and be all alone. So first of all, the first instrument to use is your eyes, and they're free. You don't have to buy them. Okay, so some things to look at. You notice the Milky Way. Look up ahead. Most times of the year, it'll be obvious by this patch of light that you'll see running across the sky. And if you can see the southern part a bit, where the center of our galaxy is, you'll actually see some of the dust lanes where the white area of the Milky Way seems to part and split into a couple paths. And that's just from the dust that's in the center plane of our galaxy that obscures our vision. And then you can get a recliner, lay on your back, see if you can identify some constellations, or maybe you'll see some star groupings that you can't identify, but sure look like they should be a constellation. There's fuzzy clusters up there you can see with your eyes. And of course, planets. Now to find the planets, they're all in the same plane of our solar system. So they'll follow the same path that the sun follows, and pretty much similar path that the moon follows. So that's generally, if you're up in the north hemisphere, you'll see them from the southwest or southeast to the southwest in an arc that the sun will follow. And one other thing, how to tell a planet from a star. Well, the stars are so far away that they're point sources, and they'll twinkle because they don't have a flat disk to sort of wash out that twinkling. So if you see a bright star and it doesn't twinkle, that's a planet. And Jupiter, or not Jupiter, but Venus gets very bright, and you could easily confuse that for an airplane. So that's usually at dawn or at dusk, because it is close to the sun, so it can't get too far from the sun. Anyway, so if you do want to spend some money on something, a standard set of binoculars is very good. And they're rated by the magnification power, that's the 10, and by the number of millimeters of the lens. So this one, for example, is 50 millimeters. Those are $50, $25, $50, something like that. And you can see amazing things with binoculars. All those fuzzy patches that you could see with your eyes, they'll resolve into stars or star clusters. Okay, now if you want to step up from that, what telescope should you buy? And a lot of people, first thing they ask is, what's the magnifying power of the telescope? And that's not the first question you should ask. The first question should be, what's the diameter of the primary mirror? Because telescopes are basically light buckets. They're collecting photons. And the bigger your bucket, bigger the opening of your bucket, the more photons you'll collect, and the fainter the object that you can see. And you can easily change the magnification on your telescope by changing the eyepiece, because the magnification is simply the telescope focal length divided by the eyepiece focal length. And that, say, the focal length of a telescope with a 6-inch or 8-inch diameter mirror is somewhere around 1,000 millimeters. And the eyepiece focal lengths run from 5 millimeters to perhaps 50 millimeters at the most. So you can go from a 200x to a 20x, and sometimes less magnification is better, because something like the Pleiades, otherwise known as the Seven Sisters, that needs low magnification to fit inside the field of view of a telescope. And in fact, sometimes binoculars work better to get a very nice image of the Pleiades, something like the Pleiades. So these are cheaper telescopes. You push those, you line it up with a Telrad finder, and I'll show you what a Telrad finder is. This is a Telrad finder. You put this on your telescope, and you look through this diagonal just with your eye. There's no magnification, and what you'll see is the night sky, a star field in the direction that you're looking, and there'll also be these concentric circles placed upon your star field. So I'll explain in a minute how to use those. But most of the telescopes come with two eyepieces, maybe 25 millimeter and a 10 millimeter, and of course you can buy other focal length eyepieces, and those can go from $30 to $300 depending on how fancy you want to get with your eyepiece, but they can be had for reasonable amounts of money. So now you have your Telrad finder, and there's a sky map with Telrad circles around cool sky objects. If you go to this link or Google Telrad circles and Messier objects or star fields, you'll see some nice charts. And for example, here's a nice chart. This is the constellation of Hercules in the middle, and Lyra, the harp or the lyre. And in here, there's the Ring Nebula. So for this one, you would put your Telrad circles so that they straddle those two bright stars, which you can see with your eyes. And then your scope is automatically pointed there. Or the Hercules, the M13 Great Star Cluster can be found that way. I'll show you what those look like. So there's M13. It's a globular star cluster. It's a group of some of the oldest stars in our galaxy. They formed a long time ago, and pretty much all at the same time. And in the telescope, it looks like a pinch of salt, like somebody dropped a pinch of salt on the table. They're quite pretty to look at. And in that other constellation Lyra, the Ring Nebula, this is what you would see in the telescope. You'd see this fuzzy shell out here in a central star. Or actually, the central star is hard to see with your naked eye, but it's also called a planetary nebula. It is a star that went through some of its evolutionary phases and sort of expelled an outer layer. A minor explosion, nothing serious. It's still illuminating. And one more, I'll give you an example of. This is the Orion Nebula. So you find this constellation of Orion, and then you get your ascending circles right there, and you get a beautiful fuzzy image of this region of gas that's glowing. So that's a wonderful image in a telescope. And just one last sight. How do you find what's above you in the area where you live? Well, there's a really nice site. It's called Heavens Above, and it has it has a menu of various objects you can look at. But you put your location in. You don't have to log in. Just put your coordinates where it is, and it'll help you find your coordinates if you don't know what they are. And then you get a nice star map like this to show you what constellations are visible. And then if you get your Telrad finder charts, then you can go find the different objects in the sky. And that's all I had.
Thank you.
Cool. Okay. We got about 10 minutes. Bill, you want to try something, or?
Sure. I just a short presentation. Let me share it. Let's see here. Wonderful. Oh, now I get something whining to me. Can you see this?
Yes.
Okay. Well, that should be good enough. Can you still?
Yes.
Okay, good. So I just want, was that?
Go on.
Okay. I just wanted to talk for a little bit about sort of the process that I go through, and I guess I hope Frank would agree, he goes through to do research, not necessarily in an observatory or using something like the Hubble Space Telescope, but more doing modeling and simulations, but also beyond that, things that you can do even if you don't know a whole lot about astronomy to get involved with doing some science. So I'm vaguely tying this together by calling it out of the observatory. I was going to say without a telescope, but there actually is an opportunity to use a telescope like we were just hearing about. So what I do primarily for my research is to use simulations. So this is where we take some system that we want to understand more about. We try and parameterize everything that we know and explore that to get some sort of new insight into that, and ideally make a prediction. Otherwise, it doesn't do a whole lot of good. So the main process we go through is you identify some sort of interesting question, and this is often the hardest part of finding a question that is both interesting and answerable. Perhaps there's been some interesting thing found. Maybe your gravitational wave detector just found some interesting wiggle, and you think you can explain where that wiggle came from. Then the next step is to actually make approximations, limit the system down to something that you can actually explain. If you want to, include every single detail in the universe and, write that down in some equation, that's going to be difficult to actually get anything useful out of. If you could simulate the entire universe, then we don't really need science. You can just figure everything out from the get-go. So you have to reduce things down. We're going to look at this star. We're going to assume it is spherically symmetric and that we could ignore this aspect and that aspect. And this is also another finer point. We've had several people that didn't notice some approximations being made with some of the statements in the class, and finding out when approximations are valid and when they aren't is an important skill to build as a scientist. Next step is actually building a model, whether that's going to be a mathematical model, whether that's going to be a computer simulation, but this is where some more technical know-how and quite often some sort of computer language or some framework is important. And then ideally you make some sort of prediction that then observers can go out and find. That's ideally how things are supposed to work. Quite often that's a little bit more challenging. So what gets happened is something unexplained happens, you come up with a model, and then you are able to reproduce what was observed, and now you have one plausible explanation. You can never prove that explanation correct, but you can try things and prove that they're wrong. This is the eternal struggle of science and why people don't like the phrase, it's only a theory. So on the right here, I'm showing a couple images that are actually from a massive simulation that was done. I was trying to get at the more or less the structure of the universe, called the Millennium Simulation Project. I linked to it where I got this image from. But so the project basically took a month of time on a supercomputer in Germany, and they just sort of put in some basic laws of physics and allowed for some dark matter.
Hey, Bill, I don't see the image.
Oh, you
don't.
have to change
You
slides.
have to move the slide down.
Oh, it's in the, oh no.
Go into presentation mode, maybe.
I'm in the presentation.
Oh,
here,
there we go.
Yeah, let me just make this as big as I can. That'll be a little bit easier.
Looks good.
So yes, this image here on the right, well, it's two images that are showing the same thing. The top one showing you more or less in the color here where the actual visible light we think would be coming from this region of galaxies. On the bottom, sort of all the colored regions there is actually where the dark matter is. And so this is showing the prevalence of dark matter and light. I mean, some of this was input into the simulation, but this is just an idea. It's a pretty picture. It can make you think simulations are really nice. It can be difficult, but it can be very rewarding when you get a nice result. So the general tack you go through this, that you sort of go from very, very simple problems all the way to as sophisticated as you need to be to try and solve a problem. You usually want to stay as low on this totem pole as possible for as long as possible because it makes things easier. So the first thing you do are these what we call back of the envelope problems, where you come up with a very rough estimate, more or less what we've been doing in these order of magnitude estimate lab problems. You can get a rough idea if your prediction for how you're going to explain some problem is right. Then if it's appropriate, you can move on to something more complicated where you're dealing with some more build aspect of your model, where you actually write something down and do some pencil and paper analysis. This is kind of, I think that by necessity, this is what most theory was for a very, very, very long time. For instance, Kepler was just looking at data, and then he did some analysis and found that, oh, it looks like these elliptical orbits actually do work very well, and he was able to make these predictions. And I believe, correct me if I'm wrong, I think Neptune was actually discovered, well, it was predicted before it was discovered, because they noticed weird things going on, some perturbations away from the purely Keplerian result for, I think it was Uranus. Someone should correct me if I'm wrong on there, but it was predicted the existence of this 8th planet before they actually found it with telescopes. It was done in this way. It's the way it's supposed to work. And then for something that's a little bit more complicated, computers get really good at doing a lot of mundane tasks. So I find myself down here in this lower left quadrant, where you're doing some sort of simple computer models that can be done on a laptop or a desktop computer over the course of hours or days. But sometimes you need to do these really, really complicated, really, really detailed things, and you need to have some time on a supercomputer like that Millennium simulation that I was just showing, where you need to get in these massive computing facilities where your computing time isn't measured in hours, but in millions of hours distributed across many machines. So you can get 1 million hours in just a few days because you're using so many different computer cores. And that's how a lot of, especially universal or galactic scale things, but even fully 3-dimensional models of stars, you can occupy a supercomputer for quite some time with the model of that. So I work more or less somewhere in between the pencil and paper and simple computer model region most of the time, but I might be moving into the supercomputer area as well. Okay, so let me switch gears and talk a little bit about citizen science. You may have heard of this. Citizen science is just this idea that even if you don't have a PhD or some particular expertise in a field, you can still contribute meaningfully to the pursuit of science. And I'm focusing on astronomy here, but there's citizen science aspects in many different fields. So in these ways, you can contribute resources you have, either your computer, your time, or your telescope in your backyard, to doing very useful things. So the first one I want to talk about is the American Association of Variable Star Observers. I believe you don't actually have to be from the US to help out with this, but I actually can't remember about that. But the AAVSO, I've had a lot of interaction with it. It's a network of amateur, I say amateur in quotes because they're usually quite capable astronomers, but they aren't professionally working as astronomers, and they just track variable stars. So any star that seems to change at night, and they'll detect novae and supernovae and all sorts of interesting things. And because they're everywhere at all times, they get really good coverage of variable stars. And so if you find if that sounds like something that's interesting, I encourage you to look into the AAVSO and try and help out with their efforts. If you have a computer and you feel shameful at night when it's just not doing anything useful when you're asleep, there's a project SETI at Home, and there's others like it that for figuring out how proteins fold, and I'm sure there's a bunch of other ones that have come out since that lets you use your computer to help this project sort of decoding what may or may not be signals in outer space. That one's a little bit more sci-fi for you, but if you're happy to donate your computer time to it, they would love to use it. And at the bottom here is normally what I would think of as citizen science, or at least the modern incarnation of it, Planet Hunters and Galaxy Zoo, and there's actually a lot of things at this zooniverse.org. I think it's sprung out of Galaxy Zoo. But these are websites where scientists have collected data, but they have so much data that they can't go through it by hand, but it's also not trivially dealt with by a computer. Usually it's some sort of classification of things where a computer cannot be easily trained to deal with it. So for instance, Galaxy Zoo has you looking at pictures of galaxies found in the Sloan Digital Sky Survey, and I believe other sources now, and classifying galaxies as various different types, and then also identifying if you see something strange. And actually they have found this strange star-forming galaxy, I think they're called green peas, was discovered by people on Galaxy Zoo that said, hey, what's this weird green dot here? And then, you know, enough times it got reported, someone's like, oh, this is something real, and this is showing up all over the place. And so then the people that work on these projects actually get acknowledged in the papers as a result of them. A little bit more contemporary or planet hunters, since right now looking for exoplanets right now is still all the rage, even with neutron stars exploding. In this case, you're looking at data and trying to find transits. And actually, I'll show some examples of what I mean. So at the top here, this is something you would be asked to find, where the citizen scientists are looking for transits. So this is when a planet passes between a star and us. So the light from the star is decreased in a very small amount, you know, like less than 1% even. We have these very sensitive telescopes, in particular the Kepler mission, that shows this tiny dip in the light as a function of time. But finding these can be difficult. And so citizen scientists go through and mark these, and then that data becomes more useful to the scientists, and they get acknowledged in papers. And then the bottom there, I'm just showing an example of a screen you would see. I just actually logged on to Galaxy Zoo, and they give you, you know, a picture of a galaxy and ask you to qualify it as, you know, an elliptical or a spiral. Is it a smooth galaxy? Is it irregular? Or is there some other weird thing in there? And you can just go through it. It's not hard. They train you in like 2 minutes, and then you can go through and do as many of these things as you want. It's kind of satisfying to just burn through a bunch of galaxies, and you feel like you've done something useful. So if you're feeling like getting interested, I encourage you to go over to zooniverse.org. Link was at the bottom here. And look at it. There's tons of projects there you can get involved with if you feel like contributing to science without necessarily, you know, setting up an automated telescope to do a bunch of work, or, you know, learning how to do a bunch of different simulations. Although we do have amateurs that help us with that as well. Okay, I think I'll stop there.
Cool. Thank you, Bill.
Mm-hmm.
Okay, we have successfully gone an hour. So I think we will sign off at this point. I guess I'll leave with a small piece of advice for the course, is that if you're looking for help on one of the lab problems, you need to be specific. You know, cut and paste a question in. Just posting, I'm having trouble, or I don't get it, it's hard to know where to start with that. Right, so happy to help, happy to give some guidance, but you have to be specific and more than just, I'm not getting it. So great, this is the first of 2. We will have one more live YouTube event in approximately 5 weeks. And so until then, we'll see you at that point. Okay, thanks everyone. Bye-bye.
Yeah, bye.